version as well. Yeah.
Okay, so area and volume conversion. Okay, so the first thing I'm going to ask is this. Do you know the tables? Are you familiar with your tables? Because that's what's going to tell us if you can do those conversions easily. Are you familiar
Ye-
with your tables?
Yeah.
Okay, so I'm going to be asking you some questions, all right? And
Mm-hmm.
then based on the questions I'm asking, um, you would I would be able to take you through how to do those conversions. All right. Now, but then before I start, apart from the conversions, are there any other areas you feel you need to brush up on?
Um, I'm not sure. Like,
Okay, you know what?
there,
Let's
there's
start
one.
with the
There's also another one. Yeah. Like, but I'm not sure what the topic is called. Where, like, say for example, you want to convert something into pints, or you want to
mhm.
convert something into. I'm not sure.
Okay.
Um,
All right. Okay. Okay. So let's see. Um, let's uh, let me see if I can get a conversion table and see if that's the one you are. Um, that's the one. Hmm. Conversion table area formula. Let me see if that is. Hold on. Hold on. Okay. Area conversion. Area conversion. Hmm. Okay. Mhm. Okay. You know what? Do you have your tables with you there?
I don't have it with me, but I think I can remember it. I think from
Can remember.
lowest, no, from highest to lowest, I think is kilo. I'm not sure of like ones in the
Okay,
middle.
hold on. Let me.
I know kilo is the like the highest conversion in that in the table I know. And then um just unit, just normal unit is in the middle. And I'm not sure what's at the bottom, but I know after unit is deci, and then after deci is centimeter. Is centi.
Okay. Okay. I think it starts with milli. That's the one you're calling the unit. Um, milli. It goes to centi, and then from centi it goes to deci, and then from deci it can now move to different ones. Okay, so let's see area area conversion. Okay, that is not what I'm looking for. Table. Okay, okay. I think this is probably what would help. Okay, so I'm going to share my screen. Let's see if this looks like what you're talking about. All right. So confirm if you can see my screen. Can you see
Hmm?
my screen?
Yeah.
Okay. Now, did you notice that, like I said, the lowest is like, it's, millimeters, right?
Pardon?
So this is for length. Can you see my screen?
Yeah.
Okay. All right. Okay. So this first one is for length. This second one is for area. Okay. So what you were is this the one you were talking about?
I think so. Yeah, yeah, yeah. That's
It
the one I
looks
was
like
talking
it.
about. Yeah, converting area units.
Okay. All right. So I'm going to maybe I should do this way. Hmm.
I think like I understand it, yeah. But like I just wanna like brush up on it just in case I forget. Cause like I know like if I was asked to do like um what's it? 2 centimeters to millimeters, like two, yeah, if I was to do like 2 centimeters to 2 milliliters, I'd have to divide it by 10.
Okay. Yeah. Yes. Yes. Now, so you know what actually determines what you divide. Okay. So let me see. I wanted to do a multiple share thing. Let me see if I can get this up. So um let's see. There we go. Okay, so we know that 10, now I'm starting with length, right? 10
Mm-hmm.
millimeters make, no, let me use equals, because actually that's what it equals 1 centimeter, right?
Mm-hmm.
Can you, can you see what I'm
Yeah.
typing? Okay,
Yeah.
good. 10 centimeters make 1 decimeter, okay? And then
Mm-hmm.
10 centimeters make 1 meter. All right. Now, um, we know that 1,000 meters make 1 kilometer. Okay.
Yeah.
Are you with this?
Yeah.
Okay. So now, based on this, right, I'm going to just show you something that's quite simple, and you can apply it to any of them. When I mean any, whether it's area, whether it's volume, whatever it is, you can apply it to all of them. Okay. So, excuse me. All right. So this is what we're going to do, right? Now, at any point in time, always look at, whenever you see the equal sign, always understand that you have a left hand side and you have a right hand side. Okay. The left hand side and the right hand side. So what do I mean by that? What I mean is this. For instance, let's look at the first one then. 10 millimeters make 1 centimeter. All right. Now, if, for instance, I had a question that said, so, um, how many millimeters are there in, say, 5 centimeters? Okay. So how many millimeters are there in 5 centimeters? How many
Pardon?
millimeters? Did you hear?
How many
Did you?
millimeters are there? Oh, 50.
Okay. So what did you do at that point?
I times it by 10.
Good. Now, if what are the possibilities of what that you may either wonder if you have to times it by 10 or divide it by 10. Okay. So
Okay.
that now I want you to just look at it from this other point of view. Now let me ask the question. Let me ask the second question. So you know that 1000 millimeters makes 1 kilometer, right?
Mm-hmm.
So we have um let me just get a random number and then okay, so 567 meters. Okay. So you're supposed to convert 567 meters to kilometers. What would you do?
Um, divide it by 4. I mean, no, 3. Divided by, no,
By
divided
what?
by 1, by 1,000. Sorry, divided by 1,000.
Okay, are you sure about that answer?
No.
Hmm? You're not sure?
Actually, yeah, I am.
Okay, good. Now, I want to ask you a question. Was it quite, why, did you have any doubt in your mind about that? Because the number that was on the left-hand side, the 567, is not a number in thousands.
Yeah, but because
You know,
it's,
it's, yes, yes, go ahead.
oh, never mind. No, no, no. I was gonna say because I know that there's 1,000 meters and 1 kilometer.
Okay, nice, nice, excellent. So now the thing is, you know why I asked that question? You have it at the back of your mind that anytime we have to convert from meters to kilometers, we would need to divide by 1000, no matter what number is involved, whether the number is in thousands, whether it's in a million, whether it's in tens, it's the same. The principle applies across board, right? It it doesn't matter what number we're dealing with. Okay. Now the next question I'm going to ask you is this. So if we were to divide 567, now you're not using. Do they allow you guys to use the calculator in your test?
Uh, it's
Do
only
they?
the, I think it's only the end of terms. It's only like the test for the end of terms and end of year test that they that
Okay, that
they do that they have a calculator paper.
nice. No, not the calculator paper, like a device, a calculator, like a calculator that could help you to do, quick sums and all that.
Oh, in
They don't
school,
let you.
yeah. In school, yeah. Like just in a casual lesson. Yeah, yeah.
Okay. Oh, okay. The casual. Okay. I know that brand. Okay. So, okay, that's nice. Okay. But you know what I usually like to do?
I
I
know.
usually like to prepare
Sorry.
myself for surprises. Okay. What if they decide that they wouldn't let you guys
Where's my
use
mom?
a calculator? Okay. What
Mm-hmm.
would you do?
It's a copy of your
Would you be
page.
able to find your way? Would you be able to figure it out?
Mm-hmm. Yeah, without a calculator, yes.
You'd be able to figure out how to convert 567 meters to kilometers. Can you do it?
Without calculator.
Yes, without a calculator.
Yeah, yeah, yeah.
Okay, so let's see. What are you going to do if you wanted to divide? Because well, it would need us to divide 507, right?
Mm-hmm.
by 1,000, isn't it?
Yeah.
Okay. So this is technically what you have there. 567 divided by 1,000. So how would you go about it?
So what I would what I would do is ow, ow, ow. What I would do is because I know there's 1 meter and 1,000 no there's 1,000 meters and 1 kilometer. So what I'll do is I'll divide the 567 by 1,000. And I know that when you divide by 1,000, it moves 3 spaces to the right. And then I'll get 0.567.
Oh, okay.
Mommy.
Okay, I think you meant it would move three spaces to the left, right? Isn't it?
Yeah.
Yeah. All right. So yes, you're right about that. So it's going to be 0.567. Okay. All right. That's fine. I just wanted to be sure that you were good with it. Okay. So all right. So let's there's something else I want to ask with regards to this, right? Now look at I need you to take a look at this table again.
That's so
Are
silly.
you hello Mason, are you there?
Yeah.
Okay. Okay. So I want you to take a look at this table once more, right?
Mm-hmm.
First one, so, we have 10 millimeters make 1 centimeter, 10 centimeters make 1 decimeter, 10 centimeters make 1 meter, 1,000 meters make 1 kilometer. Now, if we were to have a scenario like this, right?
Mm-hmm.
How many how many millimeters? Okay, so that's the question. How many millimeters are there in 1 meter? How many millimeters are there in 1 meter based on what we have here?
Um, is it 100?
No.
I mean 1,000. Sorry, 1,000. It's
Okay,
1,000.
so um, why did you say 1,000? What's the reason behind
Because
your?
I know after meter. Wait, yeah, decimeter. It's decimeter. That's centimeter. That's millimeter. Which is 3 spaces.
Okay, I'm listening. I didn't really get what you said, so you need to explain yourself.
So I know that after um I know that after 1 meter is one
Mm-hmm.
a decimeter and then 1 centimeter and then 1 millimeter and then millimeter. And that's 3 spaces. So it would be 1,000.
Okay. All right. You know how I usually do it, right? Based on
Mm-hmm.
the table, for all I need to do is to count from, millimeter. Millimeter is the question, right? How many millimeters make 1 meter? So I'll start from here
Mm-hmm.
and count. So just like you talked about counting 3 times, okay? And then I'll stop at here because meters is the destination, and this is where meters is, isn't it?
Hmm.
We have meters here, right? On the third line, isn't it?
Yes.
So yes, I would agree that it was 1,000. All right. So
Yeah.
we want to push this further, okay? So if 1,000 millimeters, right, make 1 meter, okay? Now
Mm-hmm.
the next question I'm going to ask is how many centimeters would we find in 1 kilometer?
Wait. Okay, so
Mm-hmm.
1 centimeter. So there's 10 millimeters in 1 centimeter. So
The price he gave you, just use your common sense and add like 30 pounds or 40 pounds on top. So that the person will now go and negotiate.
Now,
wait,
did you understand?
wait. Oh, sorry. Yeah, I understand. Sorry. 1 centimeter, 10 decimeter,
Mm-hmm.
100 meters, one 1,000, 1,000. Oh wait, no, it's not decameter. My bad. Oh wait, so 1 centimeter, one
Mm-hmm.
decimeter, 1 meter, one. Wait, no. Wait, 10, 10 decimeter, 100 meter, 1,000 decameter, 10,000 hectometers, 100,000 kilo. Is it 100,000
100,000. Okay, that's fine.
centimeters?
Yes, it should be 100,000. Now, I don't know. I guess you have another table with you there. But all I would have done was to follow the same principle I used for these guys. All I would have done was to start from where you have centimeters right here. Okay,
Black
that's where you
lights.
have centimeters, right? Can you see where I'm
Mm-hmm.
pointing to? Okay, so that's 10 centimeters. And go all the way to where you have. Now you can see the next one is 10 decimeters, right? Are you there meeting? You
Yeah,
muted your
I'm here.
microphone.
Oh, my bad.
Okay, so 10 centimeters, 10 decimeters, and then now we now have 1,000 meters, right? So all you just needed to do was to multiply all the numbers involved. 10 times 10 is 100. 100 times 1,000 is 100,000. Okay, so that was all I really expected. That was how I expected to go about it. But well, if you have how you go about just ensure that you're correct.
Mm-hmm.
Okay, so yeah, that's true. All right, so let's see. So this is for the length measures, right?
Mm-hmm.
Okay, so let's see. Let's play around with these two measurement factors. So let's say I have a question here, right? And I'm supposed to convert. Let's look for a number now. Ah, okay. Uh, 45 millimeters. All right. And oh, sorry, I think I meant to say millimeters. So that's
What's
mm.
the light, please?
Sorry.
No, I asked my brother to off the light.
Oh, okay. So the question is this:
Mm-hmm.
45 millimeters is how many meters? What would you do to convert 45 millimeters to meters?
So this time I wouldn't multiply. Yeah, so I would divide. So I would do. So I know millimeters at the bottom. So I'll do 40, 45 millimeters, 4.5 centimeters, 0.45 decimeters,
Uh,
and then 0.045 meters.
okay. Okay, so let me ask, how do you know exactly when to multiply and how do you know exactly when to divide? What's your guide?
So when the question is, um, so say for example, it's a smaller number. So say for example, kilometers. When they ask how many centimeters are in one
Mm,
kilometer, that's when you multiply. But if they were to ask how many, uh, what's it called? What's it called?
Kilometers.
How many kilometers are in meters?
Mm,
So
okay, you
when the
now,
what? Yeah.
yeah, go ahead. Hello, Mason, go ahead.
No, no, I wasn't saying anything.
Okay. Okay, so that's how you know when to either multiply or divide, right?
Mm-hmm.
Okay, so let's go ahead with this. So you said it's going to be 0.045, right?
Mm-hmm. Yep.
Okay, so that's as a result of dividing 45 by 1000. Okay, that's fine. All right, so I guess, so with this, do you think you can make progress on the others on your own? The area measure, the volume measure, or do you want us to go through each of them?
Pardon.
Would you like us to go ahead to the area measure now?
To begin measurement.
No, the area measure, area. This is length. This is the
Okay,
length
yeah.
measure. You want us to go to the area now?
Okay.
Okay. So for the area, right? Let me see if I'm trying to. All right. For the area, we would have 100. Okay. So now I can't even. That is the gist of it because it's area measure. I have to. I have to. Okay. So for area measure, we have 100 millimeters squared equals 1 centimeter squared. Okay. 100.
Why?
Does this look familiar?
Now. See what? But maybe see the jollof rice wrap down.
Yeah.
Does it look familiar?
Not really.
I give two. You understand?
Are you familiar?
Then you give him three.
Hello, your uncle, you're lagging.
Can you hear me now?
Yes.
Okay, good.
How did you forget to pack for Sadie?
100 centimeter squared. Um, for okay. Mhm. All right. So you said this does not look familiar.
I think it does.
Okay. So you know what? I know that some of the tables that you have may look maybe different from the ones I have. But if you can find your way around them, then I would advise that you stick to the methods that you're familiar with. Okay.
Okay.
All right. So having said that, I think I can leave you to um handle the one for volume and the one for I believe the one for area that you have. So if you still have any challenges with that, you could let me know in tomorrow's class, okay?
Okay.
All right. So today's class was supposed to we were supposed to have had it on Friday. So that was actually meant for science. So I wanted to ask, what topic are you guys doing in science right now in class? What topic are you guys doing?
In science,
Yes.
um, I think it's solid liquids and gases again. I think, and using microscopes
Mhm.
or different type of scopes to see like particles in the air.
Okay. Okay. So when you say solids, liquids, and gases, again, I'm thinking you mean you guys have done solid, liquids, and gases before.
Yeah. I
Okay.
done it in
So
primary school. I've done it like in primary, but like I only know a bit of it. I don't remember a lot because in my primary
oh,
we didn't do science.
okay, 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 okay. All right. So let's talk about the one that you guys just did recently. What did you guys learn about solid, liquids, and gases?
I can't really remember because I only had science once this week. But I remember the um what was it? I remember like how solids
Mm-hmm,
can't be moved away from each other. They're always in close contact. Uh, Liquids, what's it called? Are close together, but they're not as compact and as tight as solids. And then gases aren't together at all. And what's it
mm-hmm.
called? Um, the particles of gases have like different areas of itself because it spreads all over the room.
Excellent. Yes. So what you just said now captures um the essence of solid, liquid, and gases. And if I were to say what you just said now in a different way, right, then we would conclude
Hmm.
that solids, because they are compact and they are, the force is holding the molecule, okay, of a solid, or sorry, the atoms, not molecules, sorry about that, the atoms of a solid. The force is holding the atoms of a solid are so strong that they keep it compact, like you said. A solid has shape, isn't it?
Mm-hmm.
So did you notice that a solid has shape itself? It has a defined shape. Every solid has a defined shape. Now let's compare solids with
Mm-hmm.
liquids, right? The
Mm-hmm.
force is holding. Liquids don't have atoms. Liquids have molecules. Okay.
Mm-hmm.
So
Mm-hmm.
um, um, the forces holding those molecules in liquid are not so compact, like you said, and as tight as the ones holding solid. So what that means is liquids are freer, and because of that, liquids would would occupy the whatever container you put them in, isn't it?
Mm-hmm.
They don't have a shape of their own. They take the shape of whatever container you put them in. All right. Okay.
Yeah, yeah.
So now let's move to gases. Now gases take that property of liquids and take those properties to the extreme. meaning that the forces between the molecules of a gas are so minimal that a gas is so free, it will, like you said, it will occupy a room or a container or whatever container it is that it's in. So, and gases don't have a shape. Technically, they just occupy the space in the container, isn't it? Whatever container
Yeah.
they are in. Okay. And because they are so free to move, then you can have concepts like diffusion and all that. But I guess you guys did not go that far, so I'm not going to really talk
Oh,
about
the
that.
fusion, yeah.
Um,
Yeah. That's what we're doing. And then we learned the the you learn about the Brownian motion as well, I think.
mhm, yeah, Brownian motion. And Brownian
And
motion can be liquids, right?
mm-hmm.
Okay. So yeah. Okay. So if you were to explain the concept behind Brownian motion, what would you say is actually happening back
I
then? What
think
would you say?
what I remember is I think Brownian motion
Yeah.
is when you use a microscope to see uh I think it's something to do with gases when you see little particles of of what do you call it again, specks of dust floating in the air.
Mm. Okay. Are you talking about Brownian motion or something else?
I think is that the fusion.
Okay. Yes, diffusion has to do with movement of that molecule. Okay. From an
I can't.
area of, okay, can you hear me now?
Yeah.
Okay. So I was saying that the diffusion has to do with the movement of gas molecules or particles from an area of high concentration, right, to an area of low concentration. Did you get that?
Mm-hmm.
Okay, so now do you want to give me an example of diffusion that you know? One that you're really familiar with.
Is it? I think the ones with dust particles.
Dust particles. Okay, what else? How about when you spray a perfume?
I'm not sure about that one.
Okay,
I'm not sure about that one.
yes, excellent. Now, do you know that that's the most practical example of diffusion that you could see in everyday life? Now, I want you to
Mm-hmm.
imagine, right? You are in a room, okay, all by yourself. Now, the distance between you, where you're standing, and the door, there's quite a distance, all right? Now, at about the time you spray the perfume, I want you to imagine someone at the door, standing at the doorway, okay? Do you think that person would perceive the scent of the perfume immediately
Yeah,
if you spray it?
yeah.
Are you sure about that?
What if someone was to spray perfume?
No, you are the one spraying the perfume. You spray the perfume on yourself, okay?
Mhm.
Now, the person is standing at the door. Would the person
Is
perceive the scent
is the
of the
door
perfume?
closed?
No, no, the door is open,
Yeah,
okay?
I think they will.
Okay. Would they, now listen to my question. Would they perceive it immediately you
Not
sprayed it?
immediately.
Aha, that's what I wanted to hear. So it's not immediately. And so it takes a while, but somehow it's depending on the distance, right?
Mhm. And then
What?
uh, uh,
Yeah.
another, I think another one that we learn about is like if someone was to fart um
Yeah.
at the front of the class, after some time, the people at the back will be able to smell it.
Exactly. Exactly. That's another one. That's another practical example. right, of the diffusion. Okay, now I know we're not okay, yeah. So diffusion has to do with movement of gas, of gas, gas particles and all that. Okay, now there's another kind of movement of particles, right? But it doesn't just happen with gases. Okay, it could happen with liquids too. Okay, now let me see if it looks familiar to you. I'm going to type something on the screen. I want you to tell me if you've seen that term before. Okay,
Okay.
does it look familiar?
Osmosis, no.
Okay, it doesn't. Okay, you know what? I'm
Is
going
it
to leave it for you to
what?
discover. All right.
Is
Yes,
it
you're correct about the pronunciation.
is it something to
Okay,
do with
osmosis.
water?
Yes, it is something to do with water. Okay, so
Hmm.
but I'll leave it for you to discover. Whenever they teach you guys in class, discuss it, and I think we have a fruitful discussion if you done it in class. Okay,
I'm not
and
sure
that way
if we'll learn it like this time.
system. Oh, okay. You think it's because you guys are close to the end of the term?
Yeah.
Okay, all right. Okay, that's fine. That's fine. Okay. So now let me ask you some other questions about solid, liquid, and gases. Okay.
Okay.
Now I want you to think about this practically, right? Now, because of the compact nature, right? Yes, the background is actually noisy. If you want to change, elevate.
Hello?
Can you hear me?
Yes.
So I said, can you move away from where they're having the discussion so that you would be able to hear me better?
I can hear you. It's just because I can't go downstairs because um my father has a visitor.
Oh, okay, I understand. Okay, that's fine. But you can hear me. You're sure you can hear me.
Yeah.
Okay, good. All right. So I was saying this is what I was saying. I want you to imagine. I want you to imagine. Let's talk about how those substances, right, respond to heat. In other words,
Hello? Hello?
heat transfer in solid, liquids, and gases, right? So for solid, right?
Niggas even lagging.
Same time, it's better.
Hello, Mason. Can you hear me now?
Yeah, I can hear you.
Sorry, my network was interrupted. I think it's called.
Okay.
Okay, right. So I was saying that I was talking about transfer when it comes to solids, liquids, and gases. Do you know that when you solid, there's faster, right? And you agree with that?
Oh, you're lagging.
Can you hear me better?
Yeah, it's just because you're lagging.
I'm not. So,
And that's very clear. That's clearly very minimal because that's why she was there sitting there chatting her house, lying about something she don't get her phone. Talking about her phone debt. Talking about her phone don't get checked.
Hello?
Why are you lying?
can you hear me?
Yeah, it's just because you're lagging.
I can hear you. I'm responding immediately. I mean, there's no time difference between my questions and your answers, so I don't think there's a lag.
Because
Okay.
Okay. So I was talking about heat transfer. Did you get the scenario I put up?
Yeah.
Okay, so can you say that you practically noticed it that heat transfer is faster in solid than in liquid?
Yeah.
like, bro, she was too overly going with that one.
Can you cite an example that you noticed? Let me give you. I want you to imagine that to a car. You're standing beside a car on a hot sunny day,
Yeah, oyster.
Okay.
right? Now
Yeah.
would you notice do you notice that when you place your hand on on maybe most likely any part of the car, right? You would see
Mm-hmm.
that
The
it,
thing
it
is
would
getting
feel warm, right? And probably hot, depending on how long the car has been under the sun, isn't it?
I got a little bit
Mm-hmm.
that you made with a new friends. Do you know what I mean? Do you know what I mean? Like you have
Out of the fact that
to keep
heat
it. You know,
transfer is faster in solids, and especially metals, you know.
necessary. Like it's different. It's different if you're doing it with your friends that you've had for time, like friends that have been here since day. Which, by the way, she didn't really have. She didn't really have that thing. She's probably got like three.
You understand that this is why you don't want it. Like, not that you're controlling because you're not, but this is why your partner because she doesn't give you any reason.
Hello?
To
Did
actually.
you hear my question?
Did you go downstairs and finish off that thing?
Hello?
Did you hear my question?
No, it's because you're lagging.
Actually, the best that she can like.
Maybe I should do more typing than.
Hold on. Hold on. Wait. Let me see.
Bro, that's what she does. She literally keeps question. And
Can you repeat the question?
Okay.
You didn't even bother to do my job today.
I said the scenario that I put out to you, right? Placing your hand on a car, on the body of a car, like on a
Uh-huh.
hot sun, right? You'll notice that it heats up faster because the body of the car is a solid, and most especially because it's made of metal, right?
Mm-hmm.
Okay. So of course some solids conduct heat better than others, like solids, like metals and all that. Okay. Now now let's compare it with liquids, right?
Mm-hmm.
Now I want you to equally picture this. When you boil water in a kettle, does all the water get hot at once?
Um, no.
Why do you think it doesn't all get hot all at once?
Is it because so basically when you're boiling a kettle, normally you'll do it on a stove. So then
Mm-hmm.
when you're boiling it, before
Mm-hmm.
before the top of the water, like the peak of the water will get hot, because
Mm-hmm.
the bottom of the water is already
Mm-hmm.
making basically making contact with the hot stove, that
Yeah.
means that it'll feel the heat first.
Yes. Exactly. 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 And it will take a while to transfer that heat to the ones at the top, right?
Yes.
Thank you very much. Now, do you know that there's there's what do you call it? It takes it takes a longer while for the whole water to eventually become hot or warm, and then eventually get hot. And guess what? It's because heat transfer is not as fast in liquid as it is in solid. Okay.
Mm-hmm.
All right. Now, maybe we should not even talk about gases, but I think you'll be able to appreciate um solids and liquids because they're like stuff you deal with every day. Um,
Mm-hmm.
okay, let me just say something about gases. Now, uh, I don't know if this will okay. Do you know those what they call them hot air balloons, right?
Yeah.
What do you think is the principle that they work on? How do you think they work? How do you think they are able to stay up in the air like that?
So I think how hot air balloons stay up in the air is because basically the so hot balloons are powered by fire. So basically because the fire is like a concentrated massive flame, I think because it's a concentrated massive flame and it goes directly to like the middle of the hot air balloon, it pushes like the gases from the
Mm,
fire to
mm,
expand to expand, basically like blow up the balloon, which
mm-hmm.
pushes it up into the air, which
Oh,
is strong enough by its ropes to lift up the
mm,
basket that the humans are
oh,
in.
excellent. Excellent. That's good. Now, the fact, just to add to what you just said, the fact is the air, the gas inside the balloon it would actually heat up, right, and
Mm.
kind of expand, and it would even become lighter. It would become lighter than the air around it, and that would now make the balloon lift off. Okay, and so
Mm-hmm.
I think it's hydrogen, right? I think the gas
Mm-hmm.
in the balloon is hydrogen. That's yeah. So and hydrogen already is even lighter than the rest of air. So droplets of when you now heat it up. So yeah, that's the principle. That's a good one. So why did I take that example, right? Whenever you heat up a gas, guess what happens? It's even, the particles even move further away from themselves than ever. And that makes the gas fast and makes it lighter. Let me put it that way. Okay. So that would mean that gases become lighter when you heat them up. Did you get that?
Mm-hmm.
Okay. All right. So apart from diffusion, what other concepts did you guys talk about when it came to solids, liquids, and gases?
Uh, I can't really remember.
Okay, because you said you had it only once during the week, right?
Yeah,
Okay, good. All right.
but I
So
have
just give
it
me.
tomorrow. I have science tomorrow.
So you have science tomorrow. Okay. Okay. All right. So I guess you guys are going to talk about um you guys are going to talk about um what do you call it? You'll talk about solids, liquids, and gases some more. Okay. 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 Just give me a minute, please. All right. So I just want to reinforce what we've discussed so far. Of course, I'm sure you still learn some things from me. It's not a. I like the fact that it's an interesting topic. Do you agree?
Yeah.
Interesting topic actually. You can see the discussions that we've had so far are far reaching. Okay, can you
Mm-hmm.
see my screen?
Yeah.
Can you see my oh, good. All right, take a look
Yeah.
at let's take a closer. We've already said most of these, so I'm not going to spend time on them. Okay, guys, I know that you'd like to go to early, so you could head out early tomorrow morning. All right, so we already know states of matter, solids, liquids, and gases. And well, if we need to just say a bit about the particles that we'll find in solids, liquids, and gases, you can see for solids, they are rigid, they have a fixed shape, they have a fixed volume. Their volumes don't change. Okay. Same thing with
Mhm.
liquids. Well, not exactly. Liquids are not rigid. Liquids don't have a fixed shape. They take the shape of whatever container you put them in. And the liquids and gas and solids have in common is what? The fixed volume, right? Do you agree? Can you see that, Mason?
Yeah.
Okay, good. All right. Now let's talk about gases. Gases are not rigid. Gases have no fixed shape. I mean, can't even they just occupy, the space, whatever space they're in. And of course, gases don't have a fixed volume. We just talked about the hot air balloon. That when you heat it up, the gases do what? Expand, isn't it?
Yeah.
Yeah. All right. So let's go to the next bit. Um, um, all right. So now there are some facts here that we need to take note of. All things that you can see is made up of tiny particles called atoms or molecules. I mentioned that when I was explaining. And molecules are always moving. Take a look at that very carefully. They are always moving. They move differently depending on whether they're a solid, a liquid, or a gas. Okay. Um.
Okay.
So this is an example of matter that we can easily see three states in. Now let me say something, right? I, Let me ask you a question. Do you think all the things in this world have three states of existence? All the things you can see. Do you think, I mean, well, mm, I mean, in terms of substance, do you think that they always have three states at a time?
Uh,
Do you think you will always find solids, liquids, and gases forever?
no,
Okay. Why did you say no?
because for example,
Yeah,
you could be in
yes, go
a
ahead.
you could be in like an empty room, like just an empty room,
Mm-hmm. Yes.
and the only thing that would be in it is oxygen, which is a gas,
Mm-hmm.
and
Okay.
there won't be
So,
any liquid in the room.
okay. Okay. So let me ask you a question. Do you think it's possible for you to get liquid oxygen? Do you think it's
Liquid oxygen.
possible to get
I'm not sure.
Okay, good. I like that. I'm not sure. So the truth is this, right? If you drop the temperature, and when I mean drop the temperature, I mean really drop the temperature, you can actually get liquid from what was a gas. Okay? And if you keep
Mhm.
dropping the temperature, that liquid will eventually become a solid. That's just the principle of how water can go all the way from steam, and when you allow it to cool down, steam would turn to liquid water. And if you now put that water in the refrigerator, what happens? And leave it for a long time, what will happen?
Um,
It will become a solid, isn't it?
yeah.
That's really it. Three states of matter. And you were able to move from one state to the other by simply doing what? Dropping the temperature. And dropping the temperature simply means heat transfer, leaving the substance. Okay, so you are removing heat from it gradually. Okay, that's simply what is making it to change from one state to the other. Okay, now do you know that you can actually explain what's going on there, right? Remember, gases move randomly and move more than liquids. Do you agree with that? Gases, they are more freer to move than liquids. Do you agree?
Yes.
Okay, good. And liquids are more freer to move than solids, right?
Yes.
Okay. So what is really happening is that as you reduce the temperature of the gas, those particles that were moving, really like at random, started slowing down, and they started
Mm-hmm.
coming together. You get it, and that's the reason why they got to a point where they were so close, but they were still moving, but not like when they were fully a gas. And they came to that point where they now condensed, right, and became a liquid. Okay. Now, remember, I said liquids, their molecules are still moving, but not as random and far apart as gases. So now, the gas, remember, let's continue our story. The gas has now become a liquid, right? Has condensed and become a liquid. Now, the liquid, we're still dropping the temperature. In other words, we're removing heat from the liquid. We freeze the liquid, right? We freeze it,
Mm-hmm.
and it now becomes a solid. What really happened? Again, as you remove heat from a substance, the degree of movement, okay, of the molecules in it keeps reducing until it looks like they don't move anymore. Take note of what I said. It looks like they don't
Mm-hmm.
move anymore because of that rigid
Mm-hmm.
structure. Then you now have a solid, which in the case of water we would call ice, isn't it? Okay, we would call that ice, right?
Okay.
Yeah. Okay, so let's move on. Okay, so um, you can see what I just explained now. When you add heat, solid will change to liquid, and if you keep on adding heat, of course, if it's water, water will boil, isn't it? And it will become vapor, right? That that would mean that it became a gas. Okay, all right.
Mm-hmm.
So that's basically what happens. Of course, when you add heat, solid becomes liquid, liquid becomes gas. When you remove heat, gas becomes liquid, and liquid will also, when you keep on removing heat, liquid will become what? A solid. Okay, so just remember that adding heat would move a solid to a liquid and a liquid to a gas, while removing heat would take a gas back to a liquid and then keep on removing heat, the liquid will now become what? A solid. Okay? Did you get that?
Mm-hmm.
Okay. So now the technical name for what I just explained to you now is expansion and contraction. Expansion is what happens when the solid becomes a liquid. That's expansion. Do you agree with that? It's expanding, isn't it? Because the solid is becoming more freer to move. So it's expanding. When you're applying heat, it expands and then it now becomes liquid. Do you agree? Do you understand?
Mm-hmm.
Okay, don't worry. If any of what I'm saying sounds strange, just absorb the concept. When you get to school tomorrow, I believe you guys are going to probably take it up from here. Okay, so it would, it would kind of reinforce in your consciousness. Okay, now
Mm-hmm.
a solid has become a liquid, right? There's some expansion that has taken place there. When you keep on heating that liquid, just like you said, we put water in a kettle and put it on the stove, or a gas cooker. What happens? The liquid now becomes a gas or becomes vapor, water vapor, isn't it? Or steam. Okay.
Mm-hmm.
Now, did you notice something? That the temperature of steam is way higher than the temperature of boiling water. Do you know that? In
Mm-hmm.
fact, you would get, I don't know if it's a third-degree burn if you don't handle the steam from boiling water carefully. So anytime you are going near boiling water, you've got to make sure that you have something around your hands so that you don't, that steam must not get to your skin because it could really give you a high degree burn. You don't want that to happen. So that's a kind of precaution. So that equally reinforces the fact that it was gotten you got to steam. Why? Because you kept on applying heat. You kept on applying heat. What's the boiling point for water? Do you remember?
Is it what 90? Mm, no, it's 100 something. It's
Correct.
between
It's
one and
100. Yes, it's not between. It's exactly 100. It's
yeah.
100 degrees Celsius. Now, I know why you're thinking of between, in case the water is not pure. If it's pure, in other words, it has no impurity, then it would boil at exactly 100 degrees Celsius. Okay?
Mm-hmm.
Now, I want you to know, just like you said that the whole of the water that you put in the kettle doesn't get hot immediately. That's the same thing that's going to happen when water starts boiling. You would see it will be bubbling, right? It will be bubbling. And
Mm-hmm.
it's not the whole water that turns to vapor immediately. It gradually turns to vapor. Before you know it, the kettle will be empty. Why? Because all the liquid water has, has boiled and turned to what? Steam. And it has gone into the atmosphere, right?
Mm-hmm.
Right, mate?
Mm-hmm.
Hello.
Hello.
Okay. I didn't hear you. Hello, Mason, can you hear me?
Yeah.
Okay. Sorry, my internet acted up. Can you see my screen now?
Mm-hmm.
Okay. All right. So basically, like I said, the opposite of expansion is what? Contraction. Okay, so you can see the
Mm-hmm.
concept there. Solids and liquids expand when they get, because the particles move further apart. When they cool, they contract because the particles become closer together. And when that keeps on happening, they contract so much that it looks like, please take note, it looks like they are no longer moving because they now become rigid. Okay, and that's the part where liquids become a solid. Okay, and that's what's called freezing. Okay.
Mm-hmm.
Do you have any questions on what we've done so far?
No.
Do you have any questions?
No.
Do you have any questions?
No.
Okay. Take any notes of anything that's you probably heard for the first time.
Okay.
You didn't take notes.
Pardon?
Mason, did you say you didn't take notes?
No, I
Did you
have.
take notes? Notes. Did you write down anything?
Yes. Yeah.
Okay. Okay. Please. It's always good to take notes in class because you definitely come across stuff that you didn't know before. All right. So I think we can call it a day here.
Yeah.
Um, so that we can uh round up and go to bed on time for tomorrow. Okay.
Yeah.
So we'll meet tomorrow by 7, right? 6 your time.
Yeah.
All right.
Yeah.
It's still a one time difference between your time and our time, right? Okay,
Yeah.
nice. Okay. Okay. So have a good rest of the evening.
You too.
Okay. Have a good night. Bye.